All right, so in this first part of chapter 1, we're going to be going through quite a few sections. We'll go through sections 2, 3, 4, and 6, just a general Algebra 1 review. This is the first part. The second part will feature materials from chapter 2. But, the purpose of Algebra 2 is to continue to build on the skills that you learned in Algebra 1. So we're going to begin this year by reviewing basic algebra skills that you should remember from years before, okay? Now, the first thing we want to understand is that there's a hierarchy of number systems, and I want to take you guys through that. To begin this course. The first thing that we want to highlight is the very first set of numbers that we learn. These are called natural numbers. So natural numbers are the numbers that we begin counting with at a young age, like 1, 2, or 3. This set is symbolized or denoted by with this little double N. So this little N with the tail on the inside. So imagine. So here, let's say here is my natural numbers here. All right, so here's my natural numbers. So 1, 2, 3, and so on and so forth. Okay, then when we step out of the natural numbers, then we get into the other types of numbers that we should be familiar with. These are called, these are called integers. I-N-T-E-G-E-R-S. And this is denoted by this little double Z here. So integers are numbers that include our natural numbers 1, 2, and 3, but they also include negative numbers and the number 0. So, for example, if this is my natural numbers, then this right here is my integers. So that's 0, -1, -2, and so on and so forth. Okay. Let me zoom out just a tad here. Okay. Then we can go even further beyond that. We can go even further beyond whole numbers and get into decimals and fractions. Okay, we go into this next definition here. So the set of rational numbers, and it's denoted by a double Q. So rational numbers is the set of all all numbers that can be written as the quotient of two integers, a terminating decimal number, or a repeating decimal number. And all of those things are equivalent. Like if I can write something as a terminating decimal, it's very likely I can write it as a fraction. If I can write something as a fraction, I can write it as a repeating decimal number. Difference between terminating and repeating is, like, for example, 0.5. Terminating means, finish. Like once we get to 0.5, there's nothing past that 5. Okay, there's no other digits past the 5. So numbers like 1/2, -1/2, -1/4, 0.5, 1.3 repeating. That's what that little bar means. That tells me that these are rational numbers. They can be expressed in one of those three ways. So when we look at our universe, when we look at our mathematical universe, you got your natural numbers, you got your integers, and then you have your rational numbers. So I'm going to put 1/2. I'm going to put 0.25, 1.3333, and so on and so forth. Those are my rational numbers. Okay. We could actually go even further. There are numbers that can't be written as a quotient of two integers, as a terminating decimal, or a repeating decimal number. And basically, it's pretty much numbers that are not rational. Those are called irrational. So the set of all irrational numbers is the set of all numbers that are not rational. Now, I don't think there's any set notation for irrational numbers, at least not that I'm aware of. So I just made my own. It's going to be this double B right here. I can also, we'll talk about rational numbers in relation to real numbers in just a second. Let's see, a second here. So if this right here, if this universe is full of rational numbers, then everything outside of that is my irrational numbers, B. So that's square root of 2. Uneven square roots. So these numbers can be written as non-repeating, non-terminating decimal numbers. Like if you take the square root of 2, there's random digits that don't repeat themselves in its decimal form. Pi, 3.141, so on and so forth, that is an irrational number. And so is the number e. When we talk about exponential and logarithmic functions, the number e will play a part in that. And then, when we get all the way to the top of the list, when we take our rational numbers and our irrational numbers together, then we get this, the universe of real numbers. And the universe of real numbers is given by this double R. It's the set of all rational and irrational numbers. When we talk about domain and range, if a function has a domain or a range of all real numbers, usually this is a good answer to put down for that type of question. So that means that, like I said, the real numbers consist of everything that is rational and irrational. If it's a rational number or if it's an irrational number, then it is a real number. Now, truth be told, there's actually a set of numbers that goes even beyond real numbers, but we'll get to that when we start looking into solving quadratic equations, because that definitely plays a part in that. Okay, so in knowing these properties, so we need to be, in knowing these sets of numbers, they also have properties that are attached to it. I'm not going to go too far depth, I'm just going to give like brief examples of it. For example, so when you look at something like this, like A, B, and C, this little wonky looking E just tells me that those three numbers are in that universe of numbers. So what this means is A, B, and C are real numbers. Okay. Now, because of that, we have these properties. So then we have this first one called closure property, meaning that if I take two numbers, real numbers, and I add them together, or if I take two real numbers and I multiply them together, the result of that is going to be a real number. Like, for example, if I take 1 plus 0.5, if I add that together, that's 1.5. That's 1.5 is a rational number, which means it is a real number. If I take pi times 3, we write that as 3 pi. Now 3 pi is, 3 is a natural number. Pi is an irrational number. When I multiply those together, I get a real number. I still get a real number. Okay. Let's see, what else? Let's go down further here. Here's some more properties. Okay. If I add and multiply, again, a lot of this is multiplication and addition here. If I add two numbers, if I add or multiply two real numbers together, then they mean the same thing no matter which direction you add them. 1 plus 2 is the same as 2 plus 1. I'll use 3 pi. 3 times pi times 3 is the same thing as 3 times pi. That's called a commutative property. That's a commutative property. There's also called an associative property, meaning that it really doesn't matter what order that I add or multiply with. Like, for example, 1 plus 2 plus 3, so 1 plus 2 is 3, 3 plus 3 is 6, is the same as this, 1 plus 2 plus 3. So 2 plus 3 is 5, plus 1 is also 6. So again, that's the same thing, All right. Then we have identity and inverse properties. So when we look at identities, an identity is just something that it reveals something to itself, kind of like looking in a mirror. Like, for example, if I take 0, if I add a plus 0 or 0 plus a, I get what that number is. And same thing for multiplication. A times 1 equals 1 times a is a. So looking at properties in that context, 0 is what's called the additive identity, meaning that in addition, 0 reveals a number to itself. Same thing with multiplication. 1 is the multiplicative identity. Anything times 1 is itself. Anything plus 0 is itself. Then you have inverse properties. So inverse properties mean that if I have a real number, then there's another real number such that if I add or multiply them together, I get that identity number. In this case, we have a plus negative a. So remember, a plus negative a is the same thing as a minus itself, okay? But in the context of this property, the negative version of that number is called the additive inverse or opposite. So anytime you think of the word opposite, make sure it's in the right context. Opposite in mathematics means the negative version of that number. And of course, a times 1 over a is 1. So if I flip it into a fraction like this, it's called a multiplicative inverse or a reciprocal. Okay, number times its reciprocal is always going to be 1. And then of course you have distributive property. If I take a times a sum or a times a difference, if I distribute the a and then add or subtract, I can still get the same thing. I'll use 2, 3, and 4 for this one. So 2 times 3 plus 4, so that's 2 times 7, which is 14. 2 times 3 plus 2 times 4, so that's 6 plus 8, which is 14. Again, same thing. Same thing here. Now, let's look at some examples. Let me use this space right here. So, for example, for any situation, okay. Oh. We also have to make sure that we order these numbers correctly. Okay. So if I give an example like this. So if I have these two numbers here, let's see. I have the square root of 17 and I have 3.8. How do I know which one of these is larger or smaller? Well, I know that the square root of 16 is 4. So square root of 17, because 17 is larger than 16, square root of 17 is larger than this. Well, 4 is obviously larger than 3.8. So if this is larger than 8 and this is larger than this, that means that this number has to be greater than this number. Okay. So when we compare numbers, okay, especially when we work with number lines, we always want to make sure we put the smaller number first before the larger number. Okay, so we got to be careful about ordering numbers too, as well as their properties. All right. So now that we know different types of numbers, we also need to make sure that we know how to write and evaluate specific representations of these numbers. Okay, we'll start with what's called an expression. So an expression in mathematics is a sum, difference, product, or quotient of combinations of numbers and variables. Okay. So like, for example, 2 plus 4 is considered an expression. A plus 7 is considered an expression, okay? We can actually go even further than that and turn an expression into an equation. So what an equation is, in mathematics, it's an expression that is equal to a numerical value or another expression. That's like saying 2 plus 4 equals 6. That's an example of an equation. Or A plus 7 is equal to 5. That's another example of an equation. So first thing that we want to make sure that we remember how to do is to take an expression or take a sentence full of information and convert it to an expression. Like, for example, let's say I want to write this as an expression. So let's say 7 less than the letter T. We have to pay attention to keywords like less than, greater than, or 7 times that. Less than implies subtraction. So if I'm taking 7 less than T, what I'm doing is I'm taking that number and I'm taking 7 away from that. Okay, that's an example of an expression, right? Let me give you a fuller example. Let's say you start with $20 and save $6 each week. What algebraic expression models the total amount that you save? So you have a starting amount like this. That's your starting amount. And then each week you get $6. Okay, so that's 6 per week. Now, if you want to know how much money you make in a given amount of time, we have to come up with a variable. So we'll let this right here be our variable. We'll let W be the number of weeks that have passed. So, and per right here implies multiplication. So to find out how much money you make in a given amount of time, you take your initial amount here plus your weekly pay, 6 times W. You've just made an expression that models a situation. Okay. So then we get to more examples of expressions. If we know the numerical value of the variable, we can use substitution, in which we replace the variable with that value. And we can also combine terms that use the same variable and exponent. This is what's called evaluation. We evaluate the expression. We find the value of that expression. I'll give you an example here. So let's say that I have this expression right here. 7 times A plus 4 plus 3B minus 8. And we're going to let A be equal to -4 and B be equal to 5. Well, if I want to evaluate this expression with these variables and their values, then I'm going to substitute this number for A, this number for B. So wherever there's an A, I'm going to put this number. Wherever there's a B, I'm going to put this number, okay? So in this case, that's 7 times -4 plus 4 plus 3 times 5 minus 8. And of course, we cannot forget order of operations, right? We'll start with parentheses, then we'll work with exponents. Sorry, 7A plus 4 plus 3B minus 8, where A is -4 and B is 5. Okay, so it's 7, -4 plus 4 plus 3 times 5 minus 8. Okay, so you always start with your parentheses first, then look for evaluate any expressions with exponents, multiplication and division from left to right, addition and subtraction from left to right. Okay, we cannot forget order of operations. We're going to start here. Negative 4 plus 4, that's 0. I don't see any exponents, so now I'm going to go to multiplication and division from left to right. So this times this, and then this times this. 7 times 0, of course, anything times 0 is 0. 3 times 5 is 15, and then minus 8. And then, of course, 0 plus 15 is 15. 15 minus 8 is 7. That's the value of that expression. Okay. Now, let's say I have 7a plus 3a. As long as they have the same variable and exponent, we can combine them into 1. So that's kind of like saying 7 of this plus 3 of the same thing. Like if I have 7 cases of apples and I add 3 more cases of apples, then I end up with 10 cases of apples. So as long as the variable and the exponent on the variable is the same, you can combine those. Okay. Now, moving on to equations, okay, so using that same logic, okay, so we used order of operations to find the value of an expression. When it comes to equations, when we're solving equations, we're kind of doing the reverse of that. We're taking the reverse of those operations to find a solution to that equation. So we're solving for that variable, okay? So here, I'll give you an example. Basic example here. Let's say I have this equation. I have x plus 4 equals negative 12. So for x plus 4 equals negative 12, so I'm taking x, I'm adding 4, and I get negative 12. Well, if I want to figure out what x is, I need to reverse that operation. So instead of adding 4, I'm going to subtract 4. Now, because this is an equation, these two things are equal. So if I do something to one side of the equation, I got to do the same thing to the other side also. All right, so these two operations will cancel each other out. That's called inverse operations. 12 minus 4 is 8. I'm sorry, not 8. That's negative 12. Give me a second here. Negative 12 minus 4. Remember, negative numbers work differently than positive numbers. So if I take negative 12 and I go back 4, so imagine you have a number line here. Here's negative 12. Here's negative 11. Here's negative 13. If I'm subtracting 4, I'm moving 4 to the left. So negative 13, negative 14, negative 15, negative 16. And just like any equation, we want to make sure to check our work. Use my original equation, x plus 4. So negative 16 plus 4, so take negative 16. I'm adding 4, so I'm moving to the right. Negative 16, negative 15, negative 14, negative 13, negative 12. Negative 12, and it all checks out. It all checks out. All right. The only other thing that I want us to look at is what's called absolute value. Now, absolute value works a little bit different. It works a little bit different from a regular equation. Okay, but first I want to define what an absolute value is. Okay, so for any real number, its absolute value here. Its absolute value, which is given by this. So it's x with 2 vertical lines in between it. Okay, it is the numerical distance of that number from 0 on a number line. Now, because we're talking about distance, if you know anything about distance, you know that the distance of anything is always positive. So I'll give you an example. The absolute value of 2 is 2. It's 2 units from 0. The absolute value of negative 2, so since negative 2 is also 2 units away from 0, the absolute value is also positive 2. So if you remember anything about absolute values, okay, remember that for absolute values, all you're doing is taking the positive value of that number. So the absolute value of negative 2 is positive 2. Absolute value of regular 2 is also positive 2. Okay. Now, just because absolute value of a number is always positive, this does not mean that everything inside of the absolute value is positive. Okay. That's going to become really important, especially when we talk about absolute value equations. Okay. So just like when we're solving an equation, we're trying to isolate variables. Okay. But we cannot isolate a variable if it's an absolute value until we isolate the absolute value itself. Even when that's done, we still need to think about whether whatever's inside the absolute value is equal to the positive or negative value of that number on the other side of that equal sign. Simply because whatever's inside the absolute value could be positive or negative, the absolute value of that quantity is going to be positive regardless. Okay, and I'll show you how to do that in just a second. But we also have to make sure that whatever solutions we get, they fit back into our original equation. If they doesn't, they're what's called an extraneous solution. So let me give you an example here. I'm going to solve this equation right here. Okay, this is 3x plus 2 in absolute value minus 5 equals 4x. I'm going to solve this equation right here. All right. When I'm solving this equation, I want to isolate the variable. I want to get that variable by itself. Okay. But here's the problem with that. Okay. So when I'm solving this, I want to get this, I got to get this by itself. Okay, even though there's an x right here, I still want to get this by itself. But in order to do that, I have to isolate this. So I'm going to move this 5 to the other side. So I'm going to add 5 to both sides to cancel that out. Okay, so that leaves me with the absolute value of 3x plus 2 is equal to 4x plus 5. Now, whatever's inside this, it can be equal to either the positive value of whatever number this is, or it can be equal to the negative value of whatever this is. So whether this is equal to another expression or whether this is equal to a number, you have to split this up two ways. One where the inside is equal to the positive value of this side, or in another case where this is equal to whatever's the negative value of whatever this is. Okay, so I'm going to split this up. I have 3x plus 2 equals 4x plus 5, but I also have 3x plus 2 equals negative 4x plus 5. Again, so you got to be careful about negatives, okay? Because again, whatever 3x plus 2 is, it can either be equal to whatever number this is or the negative value of whatever number this is. Okay, so this negative is applied to the entire 4x plus 5, not just the 4x and not just the 5. We'll get to this in a minute. Let's solve this. I'm going to subtract 2 on both sides. So 3x equals 4x plus 5. I'm going to subtract negative 4x on both sides. The way that you solve equations is not going to be the same every time. You may have decided to subtract the 5 first instead of the 2. So 3 minus 4, that's negative 1x equals 5. I want x, not negative x. So I am going to, let's see. Oh, I'm sorry. I made a mistake here. This should be a 3. There we go. I forgot to actually do the subtraction. 4x plus 3. So negative x is equal to positive 3. I'm going to divide both sides by negative 1. And positive over a negative is a negative. So I got x equals negative 3. On the other side of that, the very first thing that I want to do is distribute that negative sign. So that's technically negative 1 times 4x plus negative 1 times 5. That's that distributive property that we talked about. Okay, so 3x plus 2 is equal to negative 4x minus 5. So that just changes the signs of each term in there, okay? This time, I'm going to add 4x to both sides first. Plus 4x plus 4x. So that's 7x plus 2 equals negative 5. I'm going to subtract 2 on both sides. 7x equals negative 7. Divide both sides by 7. Negative 7 divided by 7 is negative 1. So I end up with possibly two solutions here. So what I want to do with that is I want to check both of them back into our original problem to make sure that it all works out. Okay. So go ahead and erase this real quick. This is plus 5. So this is minus 5. So minus. So if I plug in negative 3 and negative 1 each into this equation, and this side is the same as this side, then we're good. Okay, then we're actually going to be good here. So we'll start with negative 3. So 3 times negative 3 plus 2 minus 5, and here's 4 times negative 3 on that side. So 3 times negative 3 is negative 9. Negative 9 plus 2 is negative 7. The absolute value of negative 7 is 7. 4 times negative 3 is negative 12. 7 minus 5 is 2. Uh-oh. I have two things that are not equal. That means that negative 3 cannot be a solution to this problem. And that's okay. It just means that it's an extraneous solution. That's okay. All right. Now let's try... now let's try the other one. Let's try negative 1. Okay. All right. So we're going to use negative 1. So that's 3 times negative 1 plus 2 minus 5, and I have 4 times negative 1 on that side. So 3 times negative 1, that's negative 3. Negative 3 plus 2 is positive 1. I'm sorry, negative 3 plus 2 is negative 1. Absolute value of negative 1 is positive 1. 1 minus 5 is negative 4. 4 times negative 1, also negative 4. Checks out. Negative 1 is our solution here.